I'm Cam. I'm from the University of Vermont. This is some work I did with a collaborator, Jakub Roslovic at Czech Technical, and he did a lot of this work, but he couldn't make it uh, to this. So I'm going to be presenting some of our work, and really, it's just a um, a set of best practices for if you want to use um, this method for designing software robots, for simulating software robots. It's called the material point method, and I'm really just going to kind of um, walk through how the method works and talk about why you might want to use it. Um, I don't know if I need to go too deeply into this at this point in the conference, um, but why would we want to use soft robots? There's many different reasons, but I think you can boil them down to kind of the human reason, maybe on the right, which is safety. If I had the option to be hit by a robot arm made out of steel or rubber, I would pick the one made out of rubber. And then maybe on the bottom left, you can kind of boil a lot of the reason why you might want to do soft robots to morphological computation. Soft materials have just a lot more intrinsic computational power. And then, of course, if we look to the biosphere, pretty much all of the organisms we observe have soft components, and for good reason. So yeah, soft robots have been simulated for a long time. It kind of dates back to the early 1900s with finite element methods, where you take a material, discretize it into a bunch of small pieces, and that makes it very easy and tractable to simulate the behavior of the material. And so then later on, there are like particle-based methods like position-based dynamics and projective dynamics. But there's all these shortcomings of each of these methods. One of them being is finite elements. Finite element methods are non-differentiable and sometimes very slow. PBD is not physically realistic because it uses sort of a predictive model to estimate system dynamics, and then projective dynamics. It's hard to model hyperelastic materials, which a lot of soft robotics does. So yeah, what's the material point method? It's a combination of a particle-based method and a grid-based method, where you basically have two different representations of your material that you switch between. And so you get the flexibility of a particle-based simulation method and the kind of computational tractability of grid operations. The material point method is differentiable. It's easy and efficient, and it's actually physically realistic. So I'm going to walk through how exactly the material point method works, and then how it and then how you can do differentiable robot design with it. So you have, in one time step, you have these three steps. And like I said, you have these two representations: a particle representation, which is basically an array of a bunch of particles, their material properties, their velocities, and their positions. And then you do a particle to grid transfer. Then you have a grid representation. You do a lot of the physical computation on that grid. And then you have a grid to particle transfer function, which puts the representation back into the particle representation for the next time step. So then, yeah, how does it work for one iteration of optimization? So you do what I just said on the last slide. For for however many time steps. You compute the loss, whatever your loss function is, if it's spanning a distance, jumping, whatever you want your robot to do. And then you backpropagate that loss through all of the physical computations that happened in the simulation. And then you update whatever parameters you're trying to optimize. These are usually like actuation parameters. But there's also been some work done where you can actually optimize the morphology of the robot, which is really cool. So then if you do what you just saw on the last slide over and over and over, for many iterations, you can get the robot to minimize your loss function and achieve the desired behavior. So I'm gonna attempt to do the smallest of live demos just to show you how easy it is to start using this. So nothing could possibly go wrong. So yeah, this repo, if you just look up like diff tai chi examples, Tai Chi is a really cool Python library that you can use to very easily do auto differentiation. And the material point method has already been implemented in this example repo. And so if you clone the repo, go into it, and then I already set up the environment. And in this diff npm.py is all of the code you would need to run a differentiable material point method simulation. So this is the actual simulation that was just on the first iteration, right? And you can watch each iteration, watch the loss go down, and everything in this diff npm.py implements the physics, implements the auto differentiation. And so I just wanted to show this to show you how easy it is to actually get started doing this if you want to use this. I want to mention while this is running, this is running just locally on my machine, and differentiable optimization of soft robots is one really good alternative to evolutionary computation, where I would have to run thousands of simulations to optimize the controller of this robot, whereas this is happening within 20 iterations of gradient descent on my local machine. So go back to my slides. So there are different ways that once you get started using this method to simulate your soft robots, there's a bunch of different things you'll run into. And this was kind of the work that this paper does, is we went through all of these things, and I just wanted to say, if you actually do want to go and use the material point method for your own research project, then go read the paper, but I'm not going to go into all of the things that we looked at. But very, very roughly, if you don't want to end up like this guy, it kind of, all the work kind of boils down to do grid search on a few parameters. And all of this stuff is in the paper, but the kind of three main parameters that you should look at is the time step size, the material point method, grid resolution, and the learning rate. So the first two will help you avoid the kind of material tearing and the robot actually being sort of physically accurate and optimizable. And then the learning rate helps you avoid things like gradient instability. Uh, and yeah, so if you actually do want to go do a research project like this, you can squeeze out yeah, better performance in less time, and not leave anything on the table when you're doing this. So yeah, the upshot is if you actually want to go and do a project with this, go check out our paper, and you'll save yourself a lot of headaches and a lot of time. And yeah, thanks to my collaborators, especially Jakob, who couldn't make it here.